At the heart of pretty much all of the computers that you've ever interacted with is electricity, but likely not in quite the way you'd think. Tiny switches control whether or not an electrical current flows through them, ultimately leaving us with two possible states: on or off. Computers represent this discrete physical information digitally using, well, digits. And because there's only two possible states, on and off, we only need two digits to represent this information, ones and zeros. This is called binary. Now, I know people often get spooked when they hear things like binary, like it's some sort of foreign complex program or secret code, and I felt this way for a long time, even after I knew enough of it to use it. Now, while I was in grad school, I had a complete epiphany. It not only demystified binary and other less commonly used number systems like hexadecimal, but it also changed my entire perspective and gave me a new level of understanding about the number system you and I use every day, base 10, the decimal system. This video serves as a standalone reference guide for any past or future videos I make where I want to reference things like hex or binary number systems and some of the underlying workings of computers and electronics. Now, this sort of thing might not be for everybody, but trust me when I say if you stick with me through this, you'll likely have your mind blown and see so much of the world in a different way for the rest of your life. First, let's understand why it is that we use a base 10 system, something that we all take for granted and never really think about. We can imagine number systems are kind of like a language, and the symbols in that number system as its alphabet. Our base 10 system has 10 characters in its quote-unquote alphabet, 0 through 9. And the fundamental reason underlying why we use base 10 all comes down to one thing: real-world physical limitations. Now, in our case, it's the fact that humans normally have 10 fingers. Now, there's nothing objectively better about base 10 compared to other number systems. It's not more accurate or objectively correct, it's simply for practical purposes. It's also no coincidence that when we're talking about individual numerals, we use the term digit, the term derived from the Latin digitus, meaning finger or toe. There's no reason to think that if humans had evolved with only 8 total fingers, that we wouldn't have ended up using octal or base 8 as our number system. As you know, even though our little number system alphabet is limited to 10 characters, we can represent essentially an infinite number of numbers, and that all comes down to how exactly we use and understand them. Even though in the context of the decimal system we're limited to 10 characters, the context or location of each individual digit carries with it implicit information that we very often forget about. Hell, the last time I thought about numbers this way was probably when I was a toddler learning numbers the first time, at which point the significance was surely lost on me. Each individual digit in a number actually carries with it two distinct pieces of information. The digit itself tells us some quantity, how many things we have, and the location of the digit within the larger context of the number itself tells us the value or size of each thing. Take a look at the number 333. Each of the digits in this number are the same. We all recognize that each individual 3 by itself is no different than any of the others, but we also understand that when seen in the context of the entire number, that each place indicates a different value. This becomes painfully obvious anytime we try to read the number out loud. It's almost subconscious to us at this point. 333 literally means 3 hundreds, 3 tens, and 3 ones. Now, of course, this pattern holds true when looking at slightly larger numbers. We know that the first digit is the number of ones, the second is the number of tens, the third is 100s, then thousands, and so on. Now, by now you've probably noticed that this is not completely arbitrary. There's a pattern here. Now, as I said before, each digit represents the quantity of things, and the digit's location in the number represents the size of each thing. Well, what's another word for size? Magnitude. You're likely familiar with the phrase order of magnitude. It's most often used in the context of the decimal system to represent factors or powers of 10. The rightmost dot is an order of magnitude larger than the middle dot, 10 times its size, and 2 orders of magnitude larger than the left dot, 100 times its size. Dealing with orders of magnitude can be extremely useful for all sorts of things, like estimations, and it's pretty simple once you understand what it means. Values at different orders of magnitude are calculated by taking the base value of your number system and raising it to the power of some factor. Now, anything to the power of 0 is 1, and anything to the power of 1 is itself. So in the context of the decimal system, 10 to the power of 0 is 1, 10 to the power of 1 is 10, 10 squared is 100, and so on. The perceptive amongst you might have figured out by now that 10 to the power of any number results in that number of zeros after the 1. 10 to the 0 power is 1 with 0 zeros. 10 to the power of 1 is 1 with 1 0. 10 squared is 1 with 2 zeros, equaling 100. Of course, this rule holds when moving in the opposite direction as well, with the negative exponent telling us how many zeros there are before the 1, including the 1 to the left of the decimal place. Both patterns continue on in either direction to infinity. Now, as a side note, this simplicity and elegance is the reason why the metric system is the preferred system of measurement by most of the world and pretty much all of the scientific community worldwide over the imperial system. And because it's based on consistent base 10 orders of magnitude, all you really need is a unit of measurement and a handful of standardized prefixes, and pretty much everybody instantly knows what we're talking about. Centi means 1/100th, so 100 centimeters is in a meter. Kilo means 1,000, so there's 1,000 meters in a kilometer. Now compare that to the imperial system. You've got 1 foot, which is 12 inches, you get 1 yard, which is 3 feet, and 1 mile, which is 5,280 feet. I'm sure there are some of you guys that are like, yeah, big whoop, I knew that. Okay then, how many centimeters are in a kilometer? When you're dealing with orders of magnitude like this, round multiples of 10, it doesn't even feel like math. You just combine the damn zeros and voila. Now, how about you tell me how many inches are in a mile? Don't worry, while you're getting a pencil and paper or digging around for your cell phone so you can pull up a calculator, I can tell you pretty easily that there's 7 million centimeters in 7 kilometers, and also tell you that your next question is going to be how many yards there are in 7 miles. Don't worry, while you're working on those, I'll carry on with the discussion. So, now that we understand why we more often than not use a base 10 system, which is largely the result of the fact that we have 10 fingers, and we understand the rules of how we represent numbers in our base 10 system, what each digit means in context, how about we take a look at different number systems to try and make it seem a little less alien to us? Now, I remember like it was yesterday, the day that my dad tried to teach me binary for the first time. Now, this was sometime in the mid to late 90s, and I was probably 7 or 8 years old. I was sitting on the couch watching a weird cartoon that I hadn't seen before called Reboot. Now, at some point, my dad must have overheard somebody in the show, one of the first ever fully CGI TV shows ever made, mention one of the characters named Hexadecimal. Now, being a software engineer who always tried to pique my interest in everything science and math related, he asked me if I knew what hexadecimal meant. Of course, other than this weird bicycle playing card Joker looking creep, I had no idea. He began by explaining to me about how the number system that I knew, the decimal system, was only one of many, and that hexadecimal, or hex, was another one that computers used. Now, given that this cartoon takes place inside of a computer system world called the mainframe, it makes sense that it would be riddled with references to all sorts of other computer technology. Hexadecimal had a sister whose name was Megabyte, and apparently they came from some uber computer virus that was previously known as Gigabyte, and some other characters included a guy named Mouse and some dude named Ray Tracer. Now, he asked me if the decimal system was based on 10, what did I think hexadecimal was based on? I, of course, had no idea. He then asked me if I knew what a hexagon was, and if so, how many sides did it have, and when I correctly told him 6, he told me the reason that it's called a hexagon was because hex refers to 6. So if decimal refers to 10 and hex refers to 6, what did I think hexadecimal was? At some point we arrived at learning that hexadecimal referred to 16, and that numbers in hex included 0 through 9 as I was used to, but also included letters. Specifically the first 6 letters of the alphabet, A through F. Now at this point, he probably saw my eyes glazing over, and in an attempt to keep me interested and try and get me to learn a bit more about numbers, he introduced me to binary. He explained that binary was a base 2 system consisting of 1s and 0s only, and asked me if I wanted to learn how to count in binary. With what I can only now assume was a big shit-eating grin on his face, he showed me this.
I can count up to 32 on 31 in one hand. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Now at this point, my mind was blown. I learned something earth-shattering on that day that I'm sure shaped the entire rest of my adult life. This was the moment that was chiseled into my brain, the point at which it became clear to me that my dad was a big fucking nerd. Of course, I had no goddamn clue what he was showing me at this point. The significance of this demonstration was entirely lost on me for over 2 decades. but I want to take this opportunity to let me try my hand at explaining what he was trying to show me all those years ago with the aid of visuals that won't instantly distract you like I was at the moment I realized my dad just gave me the finger. Now in hindsight, that was probably why he had the shit-eating grin. Yeah, well, you too, Dad. Let me introduce you now to my patented counting machine. It consists of a number of vertical sections, each with a column of lights wired up to a digital display at the bottom. This control panel over here has a button on it that, when pressed, sends a signal to the first column on the right. Each time these column of lights gets a signal, it illuminates the next unlit light. If the entire column is lit when it receives a signal, it passes the signal on to the next column and then clears all of its lights. Now the next column over that received the signal behaves exactly with the same rules as the first, filling up its lights one at a time until it's full, wherein it passes on the signal and then clears its lights. Now each time a signal is sent through this contraption, the digital displays at the bottom update to show the number of lights that are currently lit in that column. Now at any time, reading all of the digital displays together as a single number will tell you how many times that button has been pressed. Let's speed this up so we can begin to see a pattern. This allows us to visualize what counting is in a slightly different way, a bit more abstract. Because there are 10 possible values for each column, 0 lights on all the way up to 9 lights on, this counting machine was designed for a base 10 system. If we wanted to, we could adapt this design to work for literally any number system we could want. Let's try counting in hex, or base 16. Now with hex, we of course need 16 possible values for each digit, which means all the lights off is 0 and the other 15 lights for each of the digits, although this is where it gets a little interesting. If each digit has more than 10 possible values, how the hell do we represent 10 through 15 with a single digit? Well, let's recall what I learned earlier from my dad. At some point we arrived at learning that hexadecimal referred to 16, and that numbers in hex included 0 through 9 as I was used to, but also included letters, specifically the first 6 letters of the alphabet, A through F. Now that means in each position we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and then back to 0. This is what that looks like. Okay, how about we take it back to my dad's example, counting in binary. As before, let's modify our counting machine to represent a base 2 number system, meaning that we only have 2 digits to work with, 0 and 1. As we can see, the same visual pattern continues as the lights move right to left at increasingly slower rates, just with less lights to light up for each column in this case. Now the binary counting trick that my dad tried to show me when I was a kid makes much more sense. He wasn't just randomly raising fingers in arbitrary or random patterns. He was using his fingers just like the lights in my counting machine, each finger aptly representing a binary digit, with the process of putting a finger up or down being analogous to lights turning on and off. Now that we've learned counting, I'm hoping it'll be much easier for you to understand and even convert between different number systems, because you should have a deeper understanding of what each digit actually represents. Now, as an easy initial practice round, let's convert 3,419,072 in base 10 to, well, base 10. After this conversion, the numbers shouldn't change, but this will be a good demonstration of the process. Starting from the right with 0, each digit represents powers of 10, increasing by 1 for each digit. So as before, 10 to the power of 0 is 1, so this digit represents 2 times 1. 10 to the power of 1 is 10, so this digit represents 7 times 10. 10 squared is 100, so this digit represents 0 times 100. 10 to the third is 1,000, so this represents 9 times 1,000. 10 to the fourth is 10,000, so it represents 1 times 10,000. 10 to the fifth is 100,000, so here we have 4 times 100,000, and finally 10 to the sixth is 1 million. So now we've got 3 times 1 million. Now after we multiply each digit in the number with its value and add all of the results together, this gives us what we were hoping for, the original number, 3,419,072. Alright, now let's try the same thing, but this time with a binary number. Now of course before we were in base 10, so we were dealing with powers of 10, but now we're going to be dealing with powers of 2 because this is binary. 2 to the power of 0 is 1, 2 to the first power is 2, 2 squared is 4, cubed is 8, and 16, 32, 64, etc. Now, taking the binary number 1011010, we can see it's a bit easier to do this conversion, as because each number is only a 0 or 1, we can skip the multiplication. We can see that there are no 1s, 1 2, no 4s, 1 8, 1 16, no 32s, and 164. Now, adding all of these values up totals 90. Let's check our work against one of those cool online converter tools. Boom, easy peasy. Now, how about hex? Now, dealing with increasing powers of 16 and digits from 0 to f, this means a bit more work is involved in converting our number, which in this case is 3f7ba8c. C represents 12. We have 8 16s. A is 10, so we've got 10 256s. B is 11, so we've got 11 4096s. 16 to the 4th is 65,536, so that's times 7 in this case. And 16 to the 5th power is 1,048,576 times f, which is 15. And 16 to the 6th power is 16,777,216, and then times 3. So again, multiplying each digit by its value and adding everything up gives us 66,566,796. Checking one more time against an online converter shows that we are correct yet again. Now, an interesting idea worth pointing out right now is the relative efficiency of the different number systems. While we can represent all sorts of values with all sorts of different number systems, the length of those numbers, i.e. the quantity of digits that make up the number in any given base, can vary widely. This is made much more obvious when you look at the range of values that we can represent with a specified number of digits for different number systems. Now, with 8 binary digits, we can represent the values 0 through 255. With 8 decimal digits, we can represent values 0 through 99,999,999. With 8 hex digits, we can represent 0 through 4,294,967,295. As you can see, hex is far more efficient than decimal, and both are far more efficient than binary at representing different ranges of numbers given a specific length of digits. So this brings us back full circle to the idea that I opened up this video with, about binary being the language of computers. Now, as mentioned, computers, at least with our current technology, until quantum computing or some other technology replaces it, can only represent numbers at a fundamental level in binary. There's either current flowing or not, ones and zeros. Now, while this works perfectly fine for computers, especially now that we can cram literally billions of transistors onto a CPU, we just saw a demonstration about how inefficient binary was at relaying information when read by humans. Enter, once again, hexadecimal. Because 16 is a power of 2, it's both easy and efficient to represent binary values in hex, as well as being far more readable by humans. Every digit in binary is known as a bit. This literally comes from the term binary digit. Now, a group of 8 bits, like a decent-sized chunk of something you'd eat, is known as a byte. Now, of course, 4 bits, half of a byte, is aptly named a nibble. Again, let's take a look at the range of values that can be represented in 8 binary bits, or a single byte. As we learned before, 8 binary digits can hold 256 decimal values, which can be represented in hex with only 2 digits. I hope now it's a little bit more obvious why hexadecimal is both a convenient and readable way to represent the binary data that computers maintain. Now, side note here, you can see I added prefixes to these numbers. 0b being a prefix added to denote that the number after it was in binary, and 0x being a prefix denoting that the number following it was in hex. But this also holds true for other number systems with different bases as well. And because different number systems can share some of the same digits, it would be completely ambiguous what number you're actually looking at in many cases without some sort of identifier specifying what base we're dealing with. The number 1000 is, of course, 1000 in decimal, but it also means 8 in binary, 4096 in hexadecimal, and 32 in octal. Now, keep an eye out for those prefixes in the future. The next time you're able to identify a number as hex because you notice the 0x prefix, I bet you're going to feel pretty stoked. So, all of that is the foundation of how we can turn a simple electrical current into all of the complexity that we experience in things like computers and video games, and how we're able to represent that data in a human-readable format. Next time a TV show or a movie shows some cheesy hacker fella frantically typing ones and zeros into a dimly lit console, or come across a video of somebody speedrunning your favorite retro game using crazy tricks with awesome names like stale reference manipulation and arbitrary code execution, You realize that what you're looking at and what they're doing is just basically altering some internal hex values inside the computer. They're just swapping one number for another. It's no longer completely foreign to you, and hopefully you'll gain a new level of appreciation for it. Next time you're out shopping for a new shade of paint for your living room or messing around with a design in Photoshop, you'll suddenly realize how and why the colors are commonly represented the way they are. It'll hopefully make sense why black has 0 for all the 3 RGB values and all 6 hex digits, why pure red is hex FF0000, pure green is hex 00FF00, and pure blue is hex 0000FF. Why white, the shade with every color in it, has 255 for all RGB values, and how 255 should no longer seem like a totally random or arbitrary value. And also why a color like Adriatic Sea can be represented with both RGB values of 1, 96, and 129, and as hex 016081. Maybe next time you're at a work event or a party or an interview or something and you get put on the spot to show off a random or unique talent, you can put on a shit-eating grin and show them that you know how to count in binary, even if it's only so that you can give them all a finger with impunity. So I hope you learned something new and interesting from this, or at least had your perspective about the world change in some way. Now if you did, let me know down in the comments, give the video a like, consider subscribing for more thought-provoking content like this, and then maybe even share with a friend or a loved one who's going to wonder if you sent it to them because you thought they'd enjoy it, or because you wanted to have my dad flip them off. Before we end here, I wanted to give a quick shout out to my old man for always taking the time to foster my curiosity and for making me into a big fucking nerd just like him. Love you, Pops. Until next time.